Everyone, and welcome. Today we are diving deep into the ultimate rulebook of the universe. I'm talking about the laws that govern literally everything from the sun in the sky to the phone in your hand. This isn't going to be some dry, dusty physics lecture, I promise. This is thermodynamics, the absolute fundamental principles of energy. So yeah, let's get right into it. So let me ask you a question to get us started. Think about rubbing your hands together when it's cold. They get warm, right? Now picture a giant steam engine chugging along, powering a train. I mean, they seem worlds apart, but what if I told you they're both playing by the exact same set of rules? They are both, at their core, all about energy changing form. To really get a handle on these rules, we got to take a little trip back in time. See, before scientists could write the laws of thermodynamics, they had to figure out a really basic question, a huge question. What even is heat? And wow, the answer to that question completely changed everything.
You know, for the longest time, the best guess was that heat was this invisible, weightless fluid called caloric. The idea was simple. Hot things had a lot of caloric, and it would just flow over to cold things until everything was balanced. Kind of like pouring water from a full cup into an empty one. But that idea had some serious problems, which led us to what we know today. Heat isn't a thing at all. It's just energy on the move.
And the way this old idea got blown out of the water is a fantastic story. It's 1798, and this guy, Count Rumford, is watching workers bore out brass cannons. He notices that the drilling is creating a staggering amount of heat. I mean, a seemingly endless supply. And he thought, wait a minute, if heat is a fluid inside the metal, it should eventually run out. But it didn't. He had this breakthrough realization that the heat was being generated from the mechanical work of the drill. It was a game changer.
Okay, so now that we know heat is a form of energy transfer, we can finally get to the laws. And funny enough, we're going to start with the Zeroth law. Yeah, you heard me right, Zeroth. It actually came along after the first and second laws, but it was so basic, so fundamental, they had to stick it at the very beginning. You can think of it as the great equalizer.
Now, to get this law, you just need two quick ideas. First up, an adiabatic wall. Just think of it as a perfect insulator, the best coffee thermos you can possibly imagine. No heat gets in, no heat gets out. The system is totally isolated.
And the total opposite of that? That's a diathermic wall. This thing is a conductor. It's like a doorway for heat, allowing it to flow freely between two systems until they finally settle down and reach a balance. We call that balance thermal equilibrium.
And this brings us to the beautifully simple logic of the Zeroth law. Check this out. If system A is in equilibrium with system C, let's say C is a thermometer, and system B is also in equilibrium with that same thermometer, then what does that tell you about A and B? Well, it means they have to be in equilibrium with each other too.
And that single shared property, the thing that becomes equal when the heat stops flowing, that is what we officially call temperature. The Zeroth law is what gives us the very concept of temperature and proves that our thermometers are actually giving us a consistent, meaningful measurement. It's the foundation for everything else.
All right, now that we've got temperature locked down, we can move on to the first law. If the Zeroth law was the foundation, the first law is the universe's super strict accountant. It's all about the conservation of energy, and let me tell you, its books always balance. No energy ever just appears or disappears.
So to be a good accountant, we need to know how much energy a system has in its, let's call it a bank account. This is its internal energy. It's the grand total of all the random, jiggling, buzzing energy of all its molecules. And the really important thing to remember is that it only cares about the system's current state, not how it got there.
And this brings me to a really critical point. A system doesn't contain heat or work. It's not like money sitting in the vault. Instead, heat and work are the transactions. They are the deposits and the withdrawals of energy that change the balance of that internal energy account. And all this cosmic accounting gets boiled down to one of the most simple and beautiful equations in all of physics. This right here is the first law.
Let's break that down like a personal budget. Delta Q is the heat you add to the system. That's your paycheck. Now, you can do two things with that energy. You can put it into savings, which increases your internal energy, delta U, or you can spend it by doing work on your surroundings, which is delta W. Energy in has to equal energy stored plus energy spent. Period. The books have to balance.
So, if the first law sets the rules of the game, now we can look at the different plays we can run. We can change a system state by following different paths or processes, where we deliberately keep one thing constant just to see what happens to everything else.
Here are the 4 big ones. If you keep the temperature constant, that's an isothermal process. If you keep heat from getting in or out, that's adiabatic. If you lock the volume so it can't change, that's isochoric. And if you keep the pressure constant, that's isobaric. I'm not kidding. These 4 processes are like the fundamental recipes that engineers use to design pretty much every engine, air conditioner, or power plant on Earth.
And finally, we arrive at the most profound, maybe even the most famous of all the laws. The first law told us energy is always accounted for, but it never told us which way things are supposed to go. The second law, well, the second law gives us direction. It is the universe's arrow of time.
Now, this is one of the formal, official ways of saying it, called the Kelvin-Planck statement. I know, it sounds a little dense, but what it's really saying is you can't build a perfect engine. You can't just invent a machine that sucks heat out of, say, the ocean, and uses all of it to power a boat with 100% efficiency. It's impossible. You always have to dump some of that heat somewhere colder.
Here's one famous way of putting it, from a guy named Clausius. It sounds almost silly. It's so simple, right? Heat flows from hot to cold. Of course it does. An ice cube melts in your drink. Your drink doesn't get hotter by making the ice cube freeze even more. But the implication of that simple fact is gigantic. It means that all natural processes have a preferred one-way direction. They're irreversible.
And this brings us right back to our coffee. The second law is what makes things irreversible. It puts up a giant one-way sign on natural processes. Heat will always, always flow on its own from a hotter place to a colder place, never the other way around. Your coffee cooling down isn't a coincidence. It's the universe following one of its most fundamental rules. Here's what's so wild. The second law forbids a ton of things that the first law, the energy budget, would totally allow. A book on a table could, in theory, suck heat out of the table and use that energy to leap into the air. Energy would be conserved. A puddle could freeze itself on a hot day by dumping its heat into the warm pavement. Energy would be conserved. But these things never happen. The second law says no, because they would mean the total disorder of the universe spontaneously decreased. And that's the one thing that just can't happen.
And that leads us to one last big question to think about. If the first law says energy can't be created or destroyed, then why can't we build a machine that just recycles its own energy and runs forever? Why does everything eventually run down? Why do stars burn out and batteries die? The answer is hidden in the second law. Because while the quantity of energy in the universe stays the same, its quality, its ability to do useful work, is always, always decreasing. And that, right there, is a rule that governs us all.
So if the second law tells us a 100% perfect engine is impossible, that naturally leads to the next question. What is the best we can possibly do? What is the ultimate speed limit for turning heat into useful work? And this brings us to the idea of the perfect engine. The answer comes from this really elegant thought experiment from a French engineer named Sadi Carnot. The Carnot engine isn't something you can actually build in your garage. It's an idealized, totally perfect, reversible engine. It's the theoretical blueprint that operates between a hot source and a cold sink, and it sets the absolute maximum possible efficiency for any engine ever. And this ideal engine works in a beautiful 4-step cycle. First, it pulls in heat and expands. Then, it expands some more and cools down. After that, it gets compressed and dumps its waste heat out. And finally, it gets compressed even more, heating it back up to the starting point, all ready for the next cycle. And the amazing result of all this is an unbelievably simple formula for maximum efficiency. The absolute best any engine can do only depends on the temperatures of its hot source and its cold sink. That's it. The bigger the temperature difference, the more efficient your engine can be. But you can see right in the math why you can never get to 100% efficiency. To get that eta to equal 1, you need the cold temperature to be absolute 0, which is impossible. And that brings us to one last big idea. The second law, when you zoom all the way out, is really a law about increasing disorder, what physicists call entropy. Every single spontaneous thing that happens, from your coffee cooling down to a star burning out, increases the total disorder of the universe. So if this one-way street toward more and more disorder is the final rule of the game, what does that mean for the ultimate fate of the cosmos itself? It's a question that takes us from a humble cup of coffee all the way to the very end of time.